Hello class, in this video we're going to talk about two primary rules for derivatives. So I told you that my goal in this class was to teach you the definition of derivative and have you beat it into the ground to the point where you would want to see the shortcuts. And the reason for that wasn't just because I'm your teacher and I get to make your life miserable. The reason for that was because I wanted you to appreciate the shortcuts when we came to them. But we're going to go over a couple of them today. So on this slide, we will write and prove the derivative of a constant. So the function being a constant, okay, let me pick out my pen. Where's my pen? There it is. We'll go blue. So f of x equals c. Now remember, a constant is just any number. We don't have any variable. We don't have anything other than just a singular number. It could be 20, it could be 37, okay? So let's use the limit process. The limit as, not x, h. I still make that mistake. As h approaches 0, okay, it was f of x plus h. So, but remember, this is kind of a weird example because we have nothing to plug x plus h into. So f of x plus h is still just c. I'll give you an example if you're still confused of a constant function. I'd be saying f of x equals 4. That's something what our function looks like, but we're going to generalize it for all constants. So we have this part right here minus this part right here. That's just c minus c over h. And we can see this process really starts to simplify quickly because there's no distribution. There's no algebra we have to work through. We just cancel the c's and we get the limit as h approaches 0 of 0 over h. And then we can cancel this out because we got 0 in the numerator. So we got the limit as h approaches 0 of 0. And, well, the limit of any constant is the constant. So this brings us our first rule. And that's that the derivative of any constant is 0. This is quite a nice and simple rule. And we have to think about why. A constant function would just be a horizontal line. When we talk about derivatives, we're talking about helping us find the slope of the tangent line. Well, if it's a constant function, we're talking about a horizontal line. A horizontal line has 0 slope. So the slope of any point along the curve, or straight line in this case, will always be 0. So that's our first rule, and that's a nice one. And we'll go over an example later, but I want to really cover the power rule. And so this would be for if f of x equals x to the power of n. And n can be any kind of number, any real number. It can be a positive integer. It could be a negative integer. It could even be, it can't be 0. I should say that. Generally because x to the 0, we look at as being equal to 1, and the derivative of that would be 0. Although we could still technically apply it. It would just be trivial to apply it. All right, so then we got to look at the limit definition. This would be x plus h. And then we're looking at x plus h to the power of n. So limit definition, okay, as x, as h. I'm going to make that mistake the rest of the school year, aren't I? So h approaches 0 of x plus h to the power of n minus x to the power of n divided by h. Now, we have to get abstract when we're trying to prove concepts because what we have here is x plus h to the power of n. If we had an actual number for n, then we'd be able to FOIL things out. If we had, say, a negative number or we had a fractional, we have techniques for that too. Well, let's just go ahead and let's use the binomial theorem to set this up. So the limit as h approaches 0. And now here's the trick. We got to know what the binomial theorem is. If we don't know what it is, then just follow along as best we can. If you're not familiar with it, there's always been something that I say that if you don't know the binomial theorem well enough, don't resort to it. Resort to actually foiling it out. But we need the binomial theorem when we're dealing with abstract concepts. So we got x to the power of n. Now the next concept would be our binomial coefficient of n choose 1. Okay. N choose 1, but that's just n. Okay. Let me write that better. That's not very neat. Sorry, I'm still getting used to my new surface. If my writing is a little messy, I apologize. And then that would be times x to the power. Oh, I done messed up. Okay, here we go. We're on a good track. X to the power n minus 1. And then we're also going to multiply by h. And then I'll show one more term. All right. N choose 2. I'll write the binomial coefficient there. And then it's x to the power of n minus 2. And then I'll try and squeeze it in here. That's h squared, okay? And that's a dot, dot, dot. That continues. Here, I'll write the dot, dot, dot here. And then remember, we're still subtracting our x to the power of n. And this is all over h. I know that's not the best way of writing it, but when we do this, we can cancel this out and we can cancel this out. Once we do that, we have the h we can cancel. We cancel that, and each of the subsequent h's, see, I can't get it, but each of the subsequent h's will have 1 removed. Now, there's an important thing to note here. The limit as h approaches 0, once we do all that, the only term that doesn't have an h left over is this term right here. We have, well, and actually I won't write the limit here. I'll just write it equals n to the x, n times x to the n minus 1. All the others will have an h, and so we'll plug in that 0, and those will all reduce to 0, and this will be our final answer. So the derivative of x to the n is n times x to the power of n minus 1. Now, that may seem insignificant because it's just a bunch of algebraic mumbo jumbo at this moment, but let's look at a real quick example of what we're talking about. So say my function is 4x to the 5th. What I'm doing for my derivative is I'm bringing the constant down front as a multiple. That's what happened here. The n got brought down as a multiple. So now I'm doing 4 times 5. Well, that's just 20. And then I'm subtracting 1 off my exponent. So that becomes 4. And that's what's happening here. Pretty simple. All right, let's go over one. I promise I won't make you prove this one. But this is the sum and difference formula. This just tells us that if we're taking the derivative of f of x plus g of x minus, say, h of x, the derivative of this expression would be f prime of x plus g prime of x minus h prime of x. That basically means no matter what function you get, you can take each individual term as its own function, find the derivative of each individual term individually, and then just bring it back together for one problem. So let's go over an example. Okay. So here we have, use the power rule to determine the derivative of f of x equals 3x squared minus square root of x plus 4 over x squared minus 7. So what I tried to do was fit all our rules into one function so we could see this out. Now, that last rule we talked about means I can take each of these functions separately as a derivative and then bring them back together at the end. So let's do our power rule for this 3x squared. Okay. That means I'm bringing the exponent out front, and then I'm subtracting 1. So 2 times 3 is 6, and then it becomes x to the first. I'm done with that term. Now, square root of x. None of our rules discuss square root of x, but we have to remember that the square root of x is equal to x to the 1/2 power. We can convert that into a power, which means we can use our power rule. So bring that out in front. So now that's a 1/2 times x, and we have to subtract 1 off 1/2. Now, this is where you're going to have to use your knowledge of combining fractions when adding or subtracting. So 1/2 minus 1 would be a negative 1/2. Now, there's a couple ways we can simplify this. Since we've got a negative exponent, let's go ahead and kick it down to the denominator. So we got 1 over 2x to the 1/2 to make it positive. In the end result, we want everything to be positive. I've often thought that like negative exponents are best when we're using derivatives, but otherwise it's generally best to have it in rational or radical form. So I'm going to finish this off by writing equals 1 over 2 square root of x. Because once we have our final answer, we're going to want to do calculations. And 4 to the 1/2 power might seem a little weird, whereas square root of 4 is a lot easier to understand. I'll change colors for this next one. We got 4 over x squared. Now, can I bring down that 2? No, I want it to be where I can set. I don't want it to be in the denominator. If it's in the denominator, I have to use a different rule, which we haven't gone over yet. So this would be 4x to the negative 2. Okay. So I'm going to bring out my negative 2. That's 4 times negative 2 is negative 8. X, and then subtract 1 off our power. Be careful with this one. Negative 2 minus 1 is negative 3. I've seen the mistake 100 times. And now let's bring it back into the denominator to make the exponent positive. Finally, the derivative of the negative 7. This is the first rule we talked about where the derivative is just 0. Okay. So when we write our final answer, I'll write it in purple. F prime of x is 6x minus, we had the minus here, so minus 1 over 2 square root of x, and then plus, but that positive number became, or that positive term became negative. So I'm going to write it now as minus 8 over x cubed, and we're not going to have to write plus 0. This is our derivative. All right, let's go over one more in the form of another problem that's going to be common when you see it more and more throughout not only this unit, but this entire class. This is a very common question. Given the function, determine the points where a horizontal tangent line exists. So this means if we were to graph this function, we have certain points. Remember, those are always the peaks and the valleys of the graph, okay? Those points right there are where we have horizontal tangent lines. So what we always need to do first, since we're looking for horizontal tangent lines, the tool for finding the slope of tangent lines is the derivative. So we need to start by calculating the derivative. So g prime of x. Well, let's go ahead and bring the 4 out front. That's our power rule. And we'll subtract 1. So that would be 4x cubed. Okay. And then for this one, we'll do the same thing. 2 times 2 is 4, so that's minus 4. And then when we subtract 1, that is going to be x. And then here we have a constant. Sorry, I won't write. We have the constant of 2, but any derivative of a constant just reduces to 0. Okay. Now, horizontal tangent line. If we think about what we know about horizontal lines have a slope of 0. This is why this is such a common expression to go over, because it relates back to solving for the zeros of polynomials. If it's got a 0 slope, we're going to set this entire expression equal to 0. Okay? And at this point, all we need to do is factor and solve. Well, I see I've got a common factor of 4x from both terms. We're just using algebra at this point. I've just got x squared minus 1. And now I've got a difference of 2 squares. 4x times x minus 1 times x plus 1. Okay, great. And we're going to go ahead and just set those equal to 0 separately. So we'll end up with x equals 0, x equals 1, and x equals negative 1. So we have 3 points where this function would have a horizontal tangent line. Let's go ahead. All right, so let's go ahead and check on the graph. So again, these peaks and valleys right here, these little points right here are where we get those points of where the horizontal tangent line would be 0. And we can see the x value, negative 1, 0, and 1. Okay. So those are the basic rules that we're going over so far. Take some time. Remember that the homework I have assigned for you is over this entire section, and we haven't gone over this section yet. So if you see something you haven't recognized yet, that's in the future. Thanks for watching.